Today, we're going to talk about prioritized experience replay. And experience replay, if you're not familiar with the concept, is a way of storing transitions that an agent in a reinforcement learning setting has already sort of seen. This is useful because you can draw insights from past experiences, and not everything, can be taken into account immediately as you attain the reward. So perhaps the most intuitive way of training a reinforcement learning algorithm or agent would be to simply make use of the rewards and the feedback that we get from the environment and the system immediately. But there are some problems with this, namely that correlated rewards or updates break the IID assumption that many stochastic gradient-based algorithms are based on. So when the agent is interacting with an environment, if it's in some subdomain of that environment, most of the rewards are going to be quite correlated. And when we have these reinforcement learning algorithms, they are usually assuming that the feedback that we get is identically sampled from the distribution, from the entire distribution of rewards that we would expect. But if we're acting in some subdomain, then the rewards would be correlated, and that would break basically the assumptions that we're making on the algorithms. Another problem is that it rapidly discards rare experiences that would be useful to keep. So let's say you finally get a transition that's very rare when your agent interacts with the environment. You could probably learn a lot from that state. You could probably use it multiple times to train your agent. But if you discard these immediately after using them, that's not something you could take into account. So one way of getting around this problem is using experience replay. And a uniform buffer with experience replay solves both of the problems above. Basically, what the idea behind that is you have some buffer and you store the states that you were in previously in this buffer. Then you sample transitions from that identically and uniformly. So basically you pick them at random and then retrain your network using those. And then you can take in previous information into account several times. And so the correlation that we talked about before, the problem with correlation disappears because now we have a large buffer, and in that buffer, things are correlated to some extent, but significantly less than if you take consecutive updates and simply update your network based on those. There's also evidence of this kind of procedure in rodents. So within the hippocampus of rodents, it's been observed that there is similar tendencies to experience replay. And it's kind of cool that we see this sort of interplay between what we observe in biology and then also what's done in computer science. And in other domains in computer science, this is also sort of a topic that's quite heavily investigated and used. So in supervised learning, for example, there are different multiple planning algorithms and measures that people take in order to take into account previous information in a more efficient way. So we want to do the same now in reinforcement learning. And what we want to use as a gauge for what we want to replay is basically how much our agent can learn from it. So that's a very, well, from a conceptual point of view, it makes sense, but it's a very abstract notion, right? What does it mean that the agent will actually learn a lot from a transition? And in order to quantify that and make it more concrete, the TD-error would be a good candidate. So it basically tells us how surprising a transition is from the perspective of the training algorithm or the reinforcement learning agent. So that is a proxy that could be used quite, well, conceptually anyway, it seems like it could be used quite effectively to prioritize previous states. In order to make this a bit more concrete, we're going to look at an example now. So we can see up here, basically an environment of n states. The agent then is placed in state 1, needs to make it to state n and go back here. If it does so, it gets a reward of 1. And this is the only reward in the system. So you can see that the rewards that we actually have are very sparse. In either of these states, the agent can drop back to state number 1. But if it does so, then it doesn't get a reward. So this is the only one where the agent actually receives a reward. And therefore, it's going to be very hard for an algorithm that doesn't use any sort of planning to learn effectively from this architecture. So if we look at the right-hand graph here, we have a comparison between different ways of prioritizing or the experience replay that we have. So the black one here, the black line, represents uniform experience replay. So that's the buffer we discussed where we have samples of previous experience and we simply sample those at random. What this graph actually indicates is the median number of updates required in order to learn the optimal policy here. So you can actually learn the optimal policy from this environment because it's quite simple, right? And this here is basically the size of the buffer, so the number of samples. So in the case of uniform sampling, we have this sort of behavior here. This is compared to an oracle, which basically looks to greedily selects the transition that maximally reduces global loss in the current state. So this is not really a viable strategy to implement when you're learning something, because when you're learning something, you don't know what's maximally going to reduce the global loss. So this is something they did in hindsight and then sort of reconstructed what the optimal selection procedure would be. So we can see that the number of training steps required is significantly less than the black line. And so this gives us some indication that there's actually, a lot of benefit that could be realized, let's say, if you manage to create a scheme that does something similar. So we can see that there are log scales here, which basically tells us that there are orders of magnitudes of difference between these two. So it's really a massive difference between the oracle and the uniform replay scheme. As we said in the previous slide, the TD error is a good proxy, or we thought that TD error would be a good proxy because it usually tells us how surprising an update is to the algorithm. And so they did a comparison then with an actual TD error prioritization that replaced transitions with the largest absolute TD error. And this is the red line in the graph. And we can see that this also significantly outperforms the uniform one. And this is actually an algorithm that can be implemented, right? So this is a viable alternative, and we can see that we have significant, increase in performance, and that the updates needed to actually find the policy in this case is significantly reduced from the greedy policy. So we've seen now that the TD error offers significant improvement as opposed to the uniform way of basically selecting states in your replay buffer. But the TD error itself is by no means perfect. So let's say in the setting of greedy TD learning, errors will only be updated for the replay transitions. So when we prioritize our states, or basically assign them a level of TD error, which is then used for the prioritization, that assignment is only done when we actually visit the state. So if we get a low TD error for a particular state at first, it's probably going to take a long time before that's ever revisited again. So it might be good for us to actually visit that state every once in a while, even though the TD error seems to be small. But that will not be the case if we only use a greedy policy like we talked about before. Also, another problem is that greedy TD errors shrink slowly. So if you have, and this is especially the case if you use function approximators, because then you can't, let's say, update a bucket that's specific to that particular state in action. So the problem here becomes that if we have a TD error that's initially high, mainly due to, let's say, the function approximator that we're talking about, you're going to visit that state over and over again. And if it's hard to update the function approximator such that point basically reduces, then you will have a massive, let's say, concentration of visits to that particular state, which is going to cause your agent to overfit on that particular state action pair, which is not good either. And so in order to treat this, basically, you can use stochastic sampling methods. So those are, let's say, an intermediary between a greedy policy like we talked about, and then also uniform updating. So the concept is that you would assign a priority to a particular state. So that's what we denote by the small pi here. You would normalize that by all of them, and then you could add an alpha, which is basically telling you how much you would concentrate on the states that are, or focus on the states that are of high priority. And so this would allow you to basically have some trade-off between visiting states that are highly likely to contribute much, but then also having some exploration. And when you implement this, you have some degrees of freedom. So we're namely going to look at two examples here that you could do. The first one is called proportional prioritization. And then you would assign a priority like this, basically the magnitude of the TD error, so very similar to before, plus some small epsilon. And the epsilon here prevents transitions not being revisited if the error is 0. So sometimes you could be in such a state that the TD error actually comes out to be 0. Now, if you wouldn't have this epsilon, PI would be 0, and therefore you would never visit the state. But we still want to keep some probability for the reason that we talked about in the last slide. So that's why we assign an epsilon here. The second one that we're going to look at is rank-based prioritization. So there we assign basically a rank based on magnitude of the TD error, but we instead set a priority that's inverse to that particular rank. Now, what this does is it makes the algorithm a lot more robust, because we only have a ranking where we already have sort of fixed values for these different PIs. Whereas in this case, they can really range over the entire spectrum. So this one would be more robust towards outliers, but at the same time, this one is proportional. And I would say that there is more indication that a proportional assignment would be in line with what you actually want to have if you could effectively hedge yourself against the outliers. So in the same sort of graph that we saw last time, we now have these new methods as well. So to begin, the black one is the uniform one. Again, it's the median number of iterations required in the toy example that we have to learn the effective policy. The blue one is the oracle. And what we can see here is that the rank-based one and the proportional one are both similar here. There's no clear winner in terms of which one performs better than the other, but we can see that they significantly outperform the uniform algorithm again. So this is a strong indication that these schemes that we are introducing here are actually providing significant benefit for the algorithm. Now it's time to actually look at some results of these prioritization schemes. And in order to quantify the results that we get, these schemes were evaluated based on the Atari suite of games. So they're very common in the reinforcement learning space to evaluate different algorithms. What we can see on this graph, so this graph is a bit technical, we can see that we have all of the games, so the 57 games in the Atari suite outlined here. What we can see on the y-axis is the normalized score for the agent minus the normalized score for double DQN. So when we talk about normalized score, that's evaluated as per this formula here. So we have the score of our agent minus the score of just random play over the score of a human player minus the score of random play. So this is the normalized score, and we evaluate this partly for the agent that we have currently, and then also for double DQN. And so what we get is basically a histogram over these, and when the histogram is positive, that means that our current agent performs better than the double DQM algorithm. And note that the double DQM algorithm was the current state-of-the-art reinforcement learning algorithm at the time of publishing for this paper. So the comparison here is basically whether or not the scheme that we put in place is better or worse than the current state of the art. And we can see that for a majority of these ones, we basically have better performance. We have the performance for both of the schemes that we discussed. So you can see that the red ones are for the rank-based algorithm and the blue ones are for the proportional algorithm. So these come from the previous slide, right? These two methods that we had of prioritizing our replays. And so we can see that the median performance across these 57 games increased from 111% to 128%. And the mean performance went from 418% to 551%. So this is, a significant performance, both in terms of the mean performance and in terms of the median performance. And also just visually, we can see that the algorithm here tends to perform better when we put these prioritizations in place. The prioritizations variance performs similarly, as we can see. There's no major difference between the two. It's hard to say if one performs better than the other. And the authors of the paper postulate that this might have to do with the clipping of TD errors. So in order to increase stability in the algorithm, what they did when they implemented this was to clip the maximal TD error that was allowed. If you wouldn't do this, the prioritization would be so, let's say, uneven that it could easily lead to overfitting and instability in the algorithm. So that's why they did it. And they postulate that this might be a reason why we see very similar performance between the rank-based one and the other one. In order to get a fuller view of the evaluation, we're also looking at learning speed for the different algorithms. And so what we can see here on these two graphs, let's start with the left one. So this is the median across games, that is, of the maximum baseline normalized score. So what this means is the normalized score is according to the formula here, but instead of human player here, we would evaluate it using the double DQN one as a reference. So we have the normalized score, and we take the maximum of that score for a given game, and then we take the median across all games. So what this graph tells us is basically how fast the optimal or maximum score increases as a function of training steps. And as we said in the previous equation here, we would put in the double EQN algorithm. So when these ones reach 100, that basically means we're at the same level as for the double EQN algorithm. And we can see here, basically the red one is for the rank-based prioritization scheme, and the blue one is for the proportional prioritization scheme, and they both exceed the double EQN levels. And they reach the 100% level here, basically at 47 and 43% of training time. So this is a performance increase in terms of how fast it learns as well. So it doesn't just get to better final result, but it actually does so in a quicker way. If we look at the right graph now, this compares the baseline normalized score over 57 games. So, and this is the mean baseline normalized score. So we're not looking at the maximal score here generated by it, but rather, the mean score generated by each one. And we can see, as I said before, these lines here are basically when the double DQM algorithm is outperformed by the prioritization schemes. And yeah, we can see that we reach above 100 for these ones as well. And they basically get to this point at 43% and 41% of what it would take for the double DQN algorithm to converge to that point. So significant performance increase and significant increase in terms of training time. So there are definitely some, let's say, positive results from this paper. Now that we've looked at some of the learning speeds for this algorithm, we're going to look at the individual learning curves as well. So we can see those outlined here. And specifically in 41 out of 49 games, we see a significant improvement using these two prioritization schemes for the replay buffer. We have a median normalized performance across these 49 games, increasing from 48% to 106%. So that is quite a significant increase. Moreover, we have 3 games that are marked out here. So Battlezone, Frostbite, and on the next slide here, Zaxxon. For these 3 games, we can see that the new algorithms get off the ground quicker than the old ones. So we can see here for the uniform distribution or the uniform sampling, it takes quite a while for us to start converging towards a policy that actually performs well. Whereas in the case of these prioritization schemes, they seem to be doing a better job. We're going to look at 3 or 4 of these games in more detail. These ones here, we can see basically 2 things when we observe this. The first thing is that these prioritization schemes tend to generate better overall performance in the long run. So on average, that's what we saw from the metrics in the last slide as well. And this is how we would visually see it, right? So after a certain number of steps, we have a higher average reward for these 2 prioritization schemes. We can see that in the case of Alien here, it doesn't quite match the performance of a human player, but nevertheless, for other games we do. So for example, Asterix, you can see that here. Asterix is quite interesting because actually in this case, one of the prioritization schemes tends to drop in performance after a while. So that might be a problem with convergence for that particular one. The other thing we can see is similar to what we noted in let's say the overall graphs with all of the games, that this one here actually goes off the ground quicker for the prioritization schemes as opposed to the uniform sampling. So that's quite an important point actually, because a lot of these reinforcement learning tasks require substantial infrastructure in order to train them efficiently or effectively. Whatever you can do to decrease the amount of iterations required to get to convergence is obviously a good thing. And we can see here that this is quite a substantial improvement in terms of how many iterations are required. So here we're already quite close to values. I mean, close to values that are already at convergence for just the uniform sampling. And this is, at this stage for the uniform one, we barely got off the ground at all. So it's definitely a performance increase. So that's another point to keep in mind. So in conclusion, we can say that these rank-based or these prioritization schemes in general tend to outperform basically the uniform sampling from the replay memory buffer. There is no conclusive winner, let's say, between these 2. So for some of the tasks, it seems like the proportional prioritization outperforms the rank-based one, but in other cases, it seems to be inverted. It might be that for tasks where the TD error tends to have lots of outliers and be very prone to high variance, then it might be better to use the rank-based one because it's a bit more robust. And the proportional one might be better in cases where things are more controlled in a way. However, as a one-size-fits-all, there is no clear winner between them. However, it seems to be the case that both of these significantly increase performance. So in general, when constructing these kinds of algorithms, using a priority-based replay memory buffer seems to be preferable as opposed to uniform sampling from that buffer. So that's the main result of this paper. Thank you very much for watching, and see you in the next video.